Welcome students, we are back with another lesson. In this lesson, we'll discuss the dimensions. So what are the 7 dimensions? So 7 dimensions are these quantities. Okay, so what are these quantities? Now we know all our derived physical quantities. If you remember what was your derived physical quantities? So if you go back to your lesson 2, we have discussed about this derived units. Derived units means units of the derived quantities. Okay. So what were those derived quantities? These are the quantities which depends upon the 7 fundamental quantities: length, mass, time, temperature, electric current, luminous intensity, and quantity of matter. So similarly, all the derived quantities whose dimension can be expressed in some combination of the 7 fundamental quantities are known as your derived physical quantities. Okay, so the dimensions of this derived physical quantities depends upon this 7 fundamental quantities. So the dimension of the first fundamental quantity is length. The dimension of the second fundamental quantity is m. Dimension of the third fundamental quantity time is t. Similarly, for electric current, capital A; for temperature, capital K; for intensity, CD; and for the amount of substance, it is mole. Now note, whenever you write the dimensions, you write it inside a square bracket with capital letters. Fine. Except for this intensity and the substance. Rest you all write them in the capital letters. So these are the 7 fundamental dimensions. Fine. So on the basis of this 7 dimensions, we can express any physical quantity. Fine. If we do some examples, it will be more clear. Fine. From this 7 fundamental quantities, you can remember this 3 fundamental quantity. The fundamental quantity for length, mass, and time. This 3 fundamental quantity will be used more frequently. Fine. So just remember this 3. Okay. So let's take some examples to have a better understanding. So if I have to write the dimension of a density, this density is a derived physical quantity. Why? Because it depends on the 7 fundamental physical quantities. Fine. So we have to express the dimension of this density in terms of the dimension of the 7 fundamental quantities. This one: L, M, T, A, K, C, D, and mole. Fine. So how to do this? Let's see. So let's take the example of velocity. Velocity is just like speed, okay? But there is a difference between speed and velocity, which I will discuss in the upcoming chapters, not now. For now, you can consider velocity just like your speed. So the formula for velocity is the distance traveled by the object divided by the time taken to travel that much amount of distance. So distance travel upon time taken. So what will be the dimension for velocity? So your distance travel is like a length. So I'll use the unit. I'll use the dimension for length, capital L. Time taken as the dimension of time. So I'll write capital T. So the dimension is L upon T. And if I simplify, I can take this T to the numerator. Then I can write L multiplied by T to the power minus 1. Now let's write this inside this one square bracket. So I have L T to the power minus 1. Now what did I say? Whenever we will write the dimension, we will always mention our mass, your length, and your time. So let's write in terms of mass, length, and time. Now since, can you see any quantity of representing mass? No. Therefore the power of mass will be 0. Now L has a power 1. Now instead of writing 1, you can simply write L also. Okay, you can write simply L instead of every time writing to the power of 1. And then you have t to the power minus 1. This one represents t to the power minus 1. So what is the dimension for velocity? The dimension of the velocity will be m0 L to the power 1 t to the power minus 1. Fine. So acceleration can be written as change in velocity upon time taken. For now, you can just look at the formula. Okay, this physical quantities, velocity, acceleration, we will discuss it in details in our upcoming classes. Fine. For now, just concentrate on the formula and how to write the dimensions. So here you have change in velocity. Fine. Okay, so I can write this velocity as distance travel upon time taken. From here, check. I can substitute this value here, which I can write it here. Fine. Then I will write this time taken here. Okay, so the distance travel will be L, time taken will be T, and this time taken will also be T. Fine. So if I simplify this one, I can write this one as LT to the power minus 1. Okay, so I can write LT minus 1 from here. So what you notice is that instead of deriving this whole thing, can you see, instead of deriving this whole thing, if you know the dimension of velocity directly, so you can directly substitute the dimension for velocity instead of first deriving it in terms of velocity, then time. What you can do is, if you know the dimension of velocity, this one or this one, you can directly substitute this formula here. So whenever you see such a physical quantity, okay, when one physical quantity depends on the other physical quantity, then in that case what you do, directly substitute the formula. Fine. So now I will simplify this one. So if I simplify this one, I can write L t to the power minus 2, and in terms of this mlt, I can write m to the power 0 L to the power 1 t to the power minus 2. So what is the dimension for acceleration? m0 L1 t to the power minus 2. Fine. So we have learned how to derive the dimensional formula. Then we have learned from this two example that if you know the dimension of one physical quantity, you can directly substitute that dimension of the physical quantity if a situation arises in such case. So you will get this formula. Okay, let's take one more example like this one. Now let's take another example of a force. Okay, don't worry about this physical quantities. We will discuss about this physical quantities in our upcoming classes. For now, just focus on the formula, the dimensional formula, how to write this dimensional formula. Okay, so force equals to mass times acceleration. Mass dimension will be capital M. Now for acceleration, now instead of deriving the dimensional formula for acceleration, what did I say? If you know the dimensional formula for acceleration, then simply substitute this dimensional formula. Okay, instead of deriving it again, simply substitute this dimensional formula for acceleration to save your time. So if I substitute this dimensional formula, Lt to the power minus 2, so my dimensional formula can be written as m to the power 1 L to the power 1 t to the power minus 2. This is the dimensional formula for force. Fine, so you can take some as your homework. The first one is pressure. Pressure equals to force upon area. Derive the dimension formula. You should get your answer like this. Fine. Similarly, your gravitational constant. This is the formula for gravitational constant, and this is the dimension. For gravitational constant G, it is force times distance square divided by mass times mass. So its dimension, if you derive, you'll get somewhat like this. Then you have power. Power equals to work done upon time taken. Work done can be written as force multiplied with distance upon time. If you derive the dimension, you will get this one. Next is your Young modulus. So Young modulus is longitudinal stress upon longitudinal strain. Longitudinal stress is defined as force per unit area. Longitudinal stress is defined as change in length divided by total length. I can simplify and write down force times length divided by area times change in length. If you derive the dimension, you will get somewhat like this. Next is your surface tension. Surface tension sigma equals to force upon length. If you derive the formula, you will get mt to the power minus 2. Fine. So you can take this pressure, gravitational constant, power, Young modulus and surface tension as your homework. So that's it for today's class. Thank you. And if you have any confusion, please don't hesitate to ask. I will re-explain it to you again. So again, thank you.